In this video, we'll talk about isothermal ideal gas process for a closed system. On the upper right, you can see we'll have the ideal gas law we talked about in the first video. And in the upper left is the PV energy state diagram, which is pressure as a function of volume of the gas. And as I recommended in the first video, I'm recommending drawing isothermal lines, which are equivalent to lines connecting states of constant internal energy to the internal kinetic energy of the atoms or the gas molecules. Also, I always recommend drawing, as shown in the gray, a system diagram. It's kind of like the free body diagram that you do for forces, but this is a system diagram of the closed system. We're going to look at, instead of forces, we're looking at energy in the system. Isothermal means that all states between the initial state I and the final state F have the same absolute temperature. Looking at the PV energy state diagram, you can see that we have 2 points, 2 states shown. One state at volume initial, pressure initial, and the final state at volume final and pressure final. The definition of isothermal is that the initial state and the final state and all intermediate states are on the same isothermal line or isothermal curve, and therefore all states, the initial state, the final state, and all intermediate states as it progresses from the initial state to the final state also lie on this same isothermal curve. At every state intermediate between the initial and final has a constant internal energy due to the internal kinetic energy of the atoms or molecules in the system. To solve these ideal processes, we're going to be using conservation of energy, in which we'll have an energy balance equation for this closed system, which is not accelerating. This energy balance equation can be confusing because different texts and different fields use different sign conventions. I think it's very helpful and appropriate to use subscripts on both the energy as far as heat transfer and the energy as far as work transfer. The form that I prefer to use is the change in internal energy equals energy in the form of heat into the system minus energy in the form of work out of the system. An analogy would be, consider your checking account, where we'll use the units of dollars. So the change, so your system's your checking account, the change in the balance in your checking account, which is similar to the change in the internal energy, is equal to the difference between the amount in your checking account at the final state minus the initial amount in your checking account at the initial state. And that equals Q, the amount Q in would be similar to how much money you deposit into your checking account, and work out would be equivalent to minus how much you withdraw out of your checking account. So the change in the dollar balance in your checking account equals how much you net, the sum of all you put in minus the sum of all you withdraw. So in this equation, we're tracking the work out of the system into the surroundings. So the work that the system transmits out at the boundary interface between the system and the surroundings out to the surroundings. If one science convention is that they want to start tracking work out net, they would rather track the work in to the system from the surroundings, then the equation would be, an equivalent equation would be delta U equals the energy in terms of heat into the system plus the work into the system is an equivalent equation to what I'm showing. By definition, for an isothermal system, at all states between the initial state and the final state, there's the same temperature, and so therefore they're the same internal energy. The internal energy at the final state equals the internal energy at the initial state, as well as all states between. So therefore, delta U, our change in internal thermal energy due to kinetic motion, is equal to 0. Since I've defined work out of the system to the surroundings at the interface boundary between the system and the surroundings as the sign convention, this work out can be represented by the area under the PV diagram shown in the PV energy state diagram above to the upper left. So we start at volume initial and pressure initial, and then we're following the pressure up to the final pressure, and that pressure state is following the isothermal energy lines. So this integrated quantity can also be shown mathematically as the integral from the initial volume to the final volume of this term P dV. So it's the work going from state P initial, V initial to the final state P final, P final, following that path. The energy transfer in any process not only depends on the initial and final state, but also depends on the path to get from the initial state to the final state. For example, if you look at the PV diagram, if instead in following the isothermal line from the initial volume and initial pressure to the final volume and final pressure, you followed a path that deviated above or below that line at some point, the integrated quantity of the work would be different than if one followed the isothermal path between the initial state and the final state. Now we know from our ideal gas law that PV equals nRT, so simply rearranging that we can solve for P, and we can replace P, which is in this integral is changing at all intermediate states between the initial volume and the final volume, with the term nRT over V. In this equation, we can see that N, the number of moles of this gas, and R, the universal gas constant, or constant, as well as this unique case where it's isothermal, T is also constant. So I can bring those three variables outside the integral. And so I have nRT, the integral from the initial volume to the final volume of dV over V. That integral turns out to be the natural log of V. And solving from the initial volume to the final volume, we get the final equation. And so with sign convention shown, for all cases in which the final volume is less than initial volume, or in other words, systems in which the system of gas is compressed during the process, the work out of the gas is less than zero. If you go back to our system energy diagram, I'm showing at the interface boundary between the surroundings and the system that the work out of the system is negative. So the surroundings are doing work on the system, which makes sense since the case that we're showing is one in which the final volume is less than the initial volume. So the ideal gas is being compressed at all states between the initial state and the final state. And therefore, the work out of my system to my surroundings is negative. Now, arranging my energy balance equation for this closed system, or rearranging the conservation of energy law, I can solve for the energy in terms of heat into the system equals the change in internal energy of the system plus the work out net. And we know before that since it's isothermal, at all states the thermal internal energy due to the internal kinetic energy that atoms or molecules inside the system is zero. That term goes to zero. Therefore, the net energy in form of heat transfer into the system from the surroundings equals the energy in form of work out of the system into the surroundings. And since we know what that work term is, we can solve for that. Now referring to the closed system process energy state diagram shown in gray below the PV energy state diagram, it's helpful to include all the types of energy terms: the internal energy term, the energy in terms of heat transfer, and the energy in terms of work transfer, which occurs at the boundary, so at the dashed boundary between the system and the surroundings. In this case, there was no change in internal energy, but there was energy in terms of work, and since the volume of my gas decreased, the gas was compressed, as shown, the work out was negative, so there was work or energy entering my closed system. And this energy in terms of work which enters my system, which is shown in the diagram, is exactly balanced by the amount of energy in terms of heat which transfers from the system to the surroundings. So in this case, you can see that the heat energy is going out of my system to the surroundings. Therefore, the heat which I'm defining as Q into the system is also negative. Therefore, drawing both the directionality of the work and the heat and representing the magnitude by the length of these lines helps you understand what's actually happening in the system. Therefore, for this isothermal ideal gas process in which the gas is being compressed, work is entering the system and heat is leaving the system. And these two energy terms are exactly balanced. In this video, I'm showing the ideal gas process in which the gas is isothermally compressed from the initial state to the final state. If the opposite were case, where the ideal gas process were isothermally expanded from the initial state to the final state, in that case, the directionality of the work and the heat terms would be opposite direction. The energy in terms of work would therefore be out of the system into the surrounding, located at the interface between the system and the surrounding, and the energy in terms of heat would actually be into the system from the surroundings to the system at the interface boundary. And the directionality of these arrows shown in that energy state diagram would just reverse.